Thank you for your coming. I'm Simona Finessi, editor of a platform Architecture and Design, and today I'm very glad to introduce a really interesting architect and professional about the sustainability and not only. Shika Bardavash, sorry for the presentation, your name, of course. And she's a lead sustainability designer in Owings and Brown. That is one of the most important architectural firm in UK, and of course they work all around the world. And so Shika, in their 10 years of experience, has worked on many international projects with the leading architectural firms, pushing for bioclimatic design as the first approach. So when Chesai asked to focus this speech about the sustainability, it was very natural for us to thinking about this studio, this firm, and this theme of sustainability. So I don't want to spend the time about the presentation because I saw already the presentation Shika will do, and I think it's very, very interesting. So 40 minutes is a very short time to investigate a content and focus so huge as a sustainability. So I give the floor to you and welcome again. Thank you for your coming.
Um, First of all, thank you so much for inviting us to talk to you today. It is a great opportunity to be able to share our experiences with those here who are equally passionate about environmental and sustainable design. It's a real privilege. So, my name is Shikha Bhardwaj. I'm a lead sustainability designer at Hawkins Brown. My role is to lead sustainability visioning by working closely with clients to establish a shared understanding of project ambitions, the potential of the site, and with the environmental agenda always at the heart of each project. So today I'm going to talk roughly about 30 minutes about the practice, growing and integrating our sustainability team, and present a few case studies showing the whole breadth of our approach. So this is our amazing sustainability team, which is part of Hawkins Brown Specialist Design Studio that I'll talk a little bit more about. So we strongly believe in bringing diversity of people, but also perspectives and skill sets, so we can approach sustainability holistically. So for those who don't know Hawkins Brown, we are a large architecture practice of 320 staff across 5 studios. There's London, Manchester, Edinburgh in the UK, then there's Dublin in Ireland, and then LA in the US. So we work across a range of different sectors and project scales, from master plans and large infrastructure interventions like Crossrail down to small timber pavilions for community use, and then everything in between. This has meant our approach to sustainable design needs to respond to a range of different clients, contexts, and scales. But what really unites our range of projects can be filtered down into a simple concept that's flexible enough to apply to all sectors, scales, and easy for people with really little specific training to explain, which is reducing carbon and improving society. It's an evidence-based design approach to ensure our buildings enhance the lives of the future generations. So to embed these principles across the practice, we have created the SDS Studio. It's the Specialist Design Studio that spreads best practice expertise from people with all kinds of specialist skills, including digital design, BIM, visualization, and technical expertise. And sustainability sits within this group. And the power of this really is the ability to spread the knowledge, approaches, and milestone checkpoints amongst a greater number of people, so we have a much larger impact. So many times, one of the questions we are regularly asked is, how did the Hawkins Brown sustainability team and effort start, or let's say evolve? So this timeline, in a nutshell, tries to answer that. So forming staffing actually started in 2017, and the size of the team and the range of the in-house skills has been gradually increasing since then. We have also driven a commitment to reducing our business emissions as well as those in our design work by certifying our reduction plan for scopes 1, 2, and 3, and with the science-based target initiative this year. So our focus has been as a result of number of external stimuli, including various industry initiatives in the UK, regulations, and the global awareness that the situation is getting much more complex, as we know. We also believe architects have a very important real place in leading, that as we are often the lead consultants and have greater influence over design decisions. So if we know how to use it, so the more we can do in the house, the smoother the process really is. So to support our work, we have invested time and money in the development of a number of specialist in-house tools. Edgepert is a key example. In 2013, we co-funded a 4-year research project into building LCA with UCL, and in 2018 launched the first simple version of Hawkins-Brown emission reduction tool, also known as Edgepert. It basically measures embodied carbon from Revit models based on modeled materials quantities and the UK ICE databases. It is still available to download for free from our website, although it's not as sophisticated now as current tools, as the data is not very granular. So in 2020, we launched version 2 in-house, which visualizes whole life carbon, including energy and embodied, and is fully integrated with our Revit modeling protocols. This allows teams to export carbon data very quickly from their live models. We are now exploring a flexible whole life carbon tool renamed Word that we're really excited about, and that can enable quick optioneering at early design stages as well as detailed calculations, and making this available to other organizations within the UK. So this is how we do the whole process. We also invest in passive design tools as well as whole life carbon analysis, because we know it's really, really important. We have a tried and tested process when integrating sustainable design. So the first step is to fully understand the site, the context, climate, client, brief, ambition, and then we set the right targets. We then iteratively test using a range of tools and approaches. So finally, we make sure to integrate a monitoring and tracking process to make sure that the targets that are set at the early stage are not forgotten and met as the design develops. So at the project inception stage, we look at climate and site analysis even before initial proposals. We firmly believe that concepts should be driven by the site and brief combined. So we use the 3 C's, which is climate, culture, and context. We help refine the sustainability vision alongside the architectural ambition. We should always aim to have an embedded narrative or focus beyond policy and compliance. This can include big picture aspiration and practical considerations like environmental zoning, orientation, and key spatial arrangements. So iterative design and range of analysis are so important to integrating good passive and environmental design for both internal and external spaces. This is why we like to do as much in-house as possible, as we can work in an agile way and share information without any time lags. Waiting for analysis to come back and needing to make decisions quickly can really impact the final performance or optimization of a scheme, or lead to abortive work. At master plan scale, we provide input into external spaces programming and building placement and orientation. So these examples here shown are where we have been looking at the signal change in sunlight hours, so we can guide the landscape programming, design, and planting schedule. We also then used a daylight potential to guide facade development and avoid overshadowing in key spaces types. So once a master plan is more fixed or a building mass orientation confirmed, we launch into building specifics, including facade design, and primarily using solar radiation analysis. So we can give shading advice and ensure fabric performance requirements and glazing ratios mitigate overheating risks. We can also test daylight levels and glare alongside for internal comfort. Finally, we advocate for whole life carbon to be integrated in the design process. We benchmark and provide initial offsetting or budget advice. A rough idea of aspirations, outline material palette, and project abnormals will usually indicate whether it will be possible to meet the most onerous performance or not. We then use whole life carbon analysis to test options to concept stage, both of the whole life building or elements to drive reductions. And we produce detailed calculations as the building design progresses and is delivered on site. In addition, we are starting to get involved in construction processes to monitor the whole life carbon analysis as materials procurement progresses. So we also recognize that there are always more drivers than just the carbon. So we often group information on material choices into matrices. So carbon, cost, aesthetic, buildability, and other factors can be weighted in. It is rare that there is one perfect answer. And we know from our own analysis and industry benchmarking, etc., that the structure and facade are often the key indicators of meeting one target over another in regards to imported carbon. So regarding structure, there are three key material options really. One is concrete, steel, and timber, or a hybrid of the two. A decision is mostly likely to be made based on function, the clear span, the material efficiency, and hence cost, speed of construction, and potentially imported carbon. Oops. However, as you can see here, many of our projects expose chosen materials where we can for joint aesthetics and efficiency reasons. We are currently seeing more attention to optimization and material efficiency, as well as some reuse creeping in, which is really great. But the key is to emphasize this is important before specification changes like cement replacements or recycled content. So in regards to the facades, the situation is far more complex, as a case study later will show. We have almost infinite finishes and window configurations, but also need to adhere to non-combustibility and thermal performance requirements. Broadly, there are some rule of thumb we propose to our teams early, as much as if imported carbon is still in the subframing on most buildings at scale. So by reducing the cladding weight, we can reduce the use of materials, where you can use recycled products, and in regards to the finish itself, review the replacement cycle and really consider how that can be done. So moving back a step from our practice to wider issues, it's always good to remind ourselves why we are concerned with sustainable design and specifically in reducing carbon emissions and then material specifications. So globally, we need to limit the average increase of temperature to 1.5 degrees, as we all know. Nationally, we have legal commitments to be net zero carbon by 2050, with a 78% reduction by 2035. If we keep spending our carbon budget to 2050 at the current rate, we will run out many years before this. We input into the UK GBC net zero project, which indicated the policies required to maintain the reduction trajectory required to meet the 2050 targets as shown in this graphic. It is really important to our work internally within our practice that we engage as much as possible externally. Within the UK, there's a huge network of industry-led initiatives that are developing guidance and produced a policy with frequent campaigns to governments to tighten regulation and limits. So many of them that we work with are shown here with some key documentation we have fed into or co-written. They include the UK GBC, LETI, Low Energy Transformation Initiative, REBA, Whole Life Carbon Network, the NLA, and the GLA. We have won several awards for the AJ100 series recently, including Sustainability Champion, Best Use of Technology for Edgeworth, and Sustainability Initiative for a groundbreaking post-occupancy valuation. So documents shown here include embodied carbon alignment between LETI, REBA, and I-STRUCT-E, the part set campaign for regulating whole life carbon assessments, including given evidence to Parliament and the release of 2023 updates to the RICS whole life carbon assessment standard, which happened a week ago. So now I will present 4 case studies, each focusing on an aspect of sustainable design that is important to us as a practice. One is the low carbon, low energy design and passive house standards. The second is the achieving net zero carbon, integrating whole life carbon analysis and growing the circular economy. So the first case study is Agargrove, a residential regeneration project producing 500 new homes, which points to the direction of travel for the energy in use reduction to achieve net zero. This is a scheme with Camden Council that has been in our office for several years. The first phase was designed from 2013 and is completed in 2018. So right now, we are delivering the third phase. The master plan doubled the number of homes on the site while knitting the net streets and squares back into the surrounding context. At the planning stage, the council committee committed to passive house certification for all the newly built homes. So POE results for the first phase are being monitored and show that this has been achieved together with good internal comfort standards for their residents. These are the primary metrics we were designing in order to achieve the passive classic for the scheme. For the first phase, 100 homes, the passive house strategy was not a huge cost uplift. The site is next to a railway, so the noise implications required like a low U value, good air tightness, and triple glazing anyway. So the main focus for us was developing a good response to the orientation, to the form factor, and the glazing ratio. These are the key facades of the buildings, which are oriented north and south. You can see the distinct differences based on the fact that this is a heating-led scheme. The main issue for us here is to reduce space heating in the winter. The north facade has a lower glazing ratio to reduce heat losses, while the south has larger picture windows and sliding doors. These increase useful solar gain in the winter with the low sun angle, but they are protected with a continuous balcony from the highest summer sun angles and therefore protecting it from the overheating. So the key facade build-ups have been designed for low U values and to produce onerous air tightness. Agargrove Phase A mainly achieved this using a wet parch coat on the inner block leaf and with the insulation. So each facade detail and junction has to be designed with thermally broken fixings and continuous insulation lines to minimize thermal bridging, as the full length of these was used in the energy model. Then the passive house planning package was also used to model the energy loads and achieve a balance between losses and gains, as shown in this graph. The idea is that the external gains from the sun and the internal gains, like people and equipment, are used to minimize the heating load from the energy. In order to achieve this optimal balance, all building losses have to be accurately calculated. Extensive site quality checks and air tightness tests were carried out at the completion of each construction type or milestone to ensure the construction remained true to the performance parameters in the model. For example, here is shown a sill detail where a thermally broken support needed to be designed to avoid excessive pole bridging but still ensure a robust detail. Of course, we see this becoming more prevalent now as clients relearn the benefits of careful detailing and site monitoring. Our second case study is the higher education sector, the Nottingham Trent University Art and Design Building, where we managed a net zero carbon briefing process alongside the spatial briefing by the architectural team. NTU have committed to creating a net zero whole life building for their art and design school. It is a key site for the university, but with many challenges for the scale of development within the central part of the city adjacent to heritage buildings and in the conservation area. So this is how we approached the project. As first task, we looked at the spatial efficiency and future-proofing. The final brief is roughly 5,300 square meter with an occupancy of 1,100 people, supporting an overall cohort of 1,700. The size of teaching space varies from 80 to 200 square meter, and the brief to the right-hand side has developed into a collaborative spine linking teaching spaces that are as flexible as possible for changes and updates in curriculum and discipline over the coming years. So the typical plan has manifested itself in as flexible way as possible, achieving a long life, loose fit approach to the academic spaces around the social core. The idea here is that each of these areas is as column free as possible and could be refitted in the future for a variety of purposes. The efficient core has the fire separated scissor as shown on the right staircase to achieve the two directions of escape required on the same building footprint. So coupled with this are the university's ambitions performance standards responding to the Council's carbon neutral pledge. During the design stage and to planning, NT committed to delivering the building as net zero whole life carbon to support Nottingham Council 2028 targets. The university is ranked as one of the greenest universities in the UK and for the past 8 years and is amongst the world's most sustainable universities. So to ensure the university knew what they were getting themselves into, which is always a good idea, we dedicated carbon workshops to enable decision making around targets and material choices. These were much decisions at the early design stages about the definition of net zero, and NTU were adamant that they wanted to extend the meaning to whole life, excluding embodied carbon. So this chart here shows how the design iterations have gradually driven the whole life carbon metrics of the project, measured over a 60-year period and balancing operational carbon and embodied carbon. These high-level graphs were really useful for communicating the nuances of the scheme quickly to a high-level audience from a steering group. So in regards to embodied carbon, at the early design stage, we took an external elemental approach to reducing this. This graph shows these structural systems compared in terms of their total carbon emission. It is worth noting here that due to the combustibility and insurance issues, which we're finding a lot, it's coming up a lot on the projects at the moment, timber as a structural solution was completely omitted early on. So concrete was chosen as it offers thermal mass benefits when exposed, helping to minimize energy in use as well. The challenge was to refine the design, use as little material as possible, and then review the specifications. We eliminated the basement, made sure the grid was not excessive, omitted transfer structure where possible, and proposed post-tension slabs to minimize depth and reinforcement quantities. We did explore cement replacement, but the university was not confident and would not commit. We then looked at facades. This graph shows the facades options we tested over the A to C boundaries, excluding B6 and B7, which is basically energy and water. There is where replacement cycles come into play, and you have to be careful to balance the carbon put into the project upfront versus the carbon emitted over the whole expected life cycle of a building. So ceramics was chosen as the main material as it matches the civic, crafted and artisanal expression for the building, as well as having an extremely long life. The client and team liked the texture and the ductility offered. Some parts of the building will be rendered, recognizing the low upfront carbon value of this treatment, but the requirement for regular maintenance. Within the ceramic cladding on the market, there's a huge range of carbon emissions in themselves. The profile, density, weight, and support structure required all affects the embodied carbon. So once a material is chosen, it is important to keep asking for EPTs and testing the carbon throughout the design stages. Finally, as a last task on this project, we ensured all materials in the specification that has a significant effect on the whole life carbon model were indicated in the tender material, so the delivery of the scheme could be aligned with the estimation made at design stage. Golden Lane is one large retrofit project of about 15,000 square meter of speculative commercial workspace near the Barbican with a client Castleforge. We are retaining 96% of the structure while adding 4 stories without foundation strengthening. So sustainability has been a key driver for the client with a variety of certifications undertaken and the desire to get the project recognized as net zero within the current UK GBC framework. So we did like a lot of carbon comparisons here. So this graph shows the comparison between aluminium cladding with GRC over 60 years reference period. We expected that the GRC would actually prove to be saving a lot of carbon, but at stage 3, they were actually really similar. This was because although the GRC itself is a low carbon and lasts a long time, the proposed build-up required a lot of steel framing to hold it up that added to the embodied carbon of the whole detail. And although the aluminium needed more frequent replacement or maintenance, this did not outweigh the steel framing of the GRC. An interesting finding was that if a maintenance regime could be guaranteed for the aluminium to be repainted only during maintenance and not fully replaced, a further saving could be made. But this would need the builder owner to lock this in to achieve the saving and is by no means guaranteed. Equally, looking at the material breakdown, the steel supports for the GRC were by far the highest emissions. So reducing this or guaranteeing a recycled source for the steel framing would have brought in below that for the aluminium system. And because GRC was preferred facade material within the context of stage 4, design focused on reducing the embodied carbon of the framing by refining the support design. So this slide summarizes the whole process. What has been really fascinating has been tracking the embodied carbon through the design process and seeing the impact of the decisions on the figure. Early in the design, more reuse was hoped for. The team was looking at overcladding a large part of the existing facade, but this was not feasible due to the lack of the cavity barriers and instability of the brickwork. It would need more embodied carbon and the cost to hold it up than rebuilding, unfortunately. We even explored crushing the original brick for the new precast plinth cladding, but the grain was unworkable. However, when we have reused it, is the raised access floor and steel work deconstructed from the old building in the extension. So early on, we explored timber was the extension, but the composite deck made the escape strategy easier, meaning retention of the existing cores. So nothing in an existing building is straightforward, really. You can see the reduction made from stage 3 and 4 as these options were explored and made viable. So a final case study looks at reuse, so modular construction and design for deconstruction. Teddy London is an etchy engineering enterprise co-founded by 3 global universities, King's College London, Arizona State University, and UNSW Sydney. It was built at British Lands Canada Water Development, constructed from reused volumetric modules, and is designed to be deconstructed at the end of life for future use. This is a planned for event as the campus will only be here for up to say 7 years, but effort was also spent ensuring an overall enhancement on the site and student experience. These are the images of the first phase. All materials can be stripped off and separated for use elsewhere. Built in the UK, the building itself took just 6 weeks to construct once the modular components had arrived on the site, minimizing disruption to the local area. So each module uses lightweight steel frame boxes clad with insulation and requires no deep piles or concrete. So the second phase, which was completed this summer, used the techniques from the first phase that worked, but also utilized reused modular units. By working with a company called Premier Module, they were able to produce schedules and drawings of the units available to the space planning, and facade could be designed around the pre-made openings. So some windows are also reused from the stock. This is another good example in longevity of specifications. If you know the life cycle of a product will be less than its service life, either design it to be reused elsewhere or specify low carbon materials that only last as long as you need them to avoid excess upfront emissions. Equally, for those in place for a long time, reduce replacement times. For our conclusion, basically, I spoke a lot, but there is no right answer. We must think through our choices is key at every design stage and life cycle stage through a number of lenses. And we must advocate for architects as lead consultants to take control of each design, drive through passive design, fabric first, and energy efficiency measures, and lead the conversation on materials. While the sub and superstructure is the largest proportion of embodied carbon in the building, the architect is still the curator of the design and has the widest influence over a holistic decision, balancing all the factors. It also has to be recognized that there is no perfect answer along with the right answer. The lowest carbon option is not to build at all. But we all know that this is an unlikely the full solution. So we must build less by retrofitting and reusing. And we need to be efficient with the material by using the right thing for the right job. Thank you. This is the last slide.
Thank you so much. Very interesting and very scientific approach. So before to ask if anybody want to ask something to you, I'm wondering, so in your experience, as the awareness of the customers, your customers, is growing, because I mean, the sustainability approach is difficult, is probably it needs more effort in the process, probably more expensive, probably. So it's a real growing the awareness of your customers what it means exactly to have a sustainability approach in the project.
Well, I think I wouldn't fully agree with you when you say sustainability is complex, because when we go back and look at vernacular architecture, all the strategies are embedded in a vernacular architecture. They looked at the sun path, they looked at the orientation, they made sure, the energy efficiency was embedded within everything was built. But I think it's the way we now approach construction industry, where, everything is built to fulfill certain briefs and certain requirements. We've forgotten that something we were really good at doing, in the past. But in terms of what we mean by sustainability within Hawkins Brown and how we embed that is a conversation, is having a dialogue with the client. It's starting the process. So we never walk into a meeting room and say, this is a list of 10 things, do this, and your building is sustainable. No, it's more like, let's understand what your building requires, how it's good for the planet, for the people, and also, in the end, there's a commercial aspect to it, so you need to strike a balance. But it's just taking it from there, step by step, defining the aspects, the targets, the KPIs, and how you can quantify sustainability. You take it from there, and then you set the process, and you sort of basically follow it through the different design stages.
Thank you. Any questions? Don't be afraid. It's easy. It's easier to ask than answer. Okay.
Thanks for your presentation. I'm Marco from Open Project in Bologna, architecture engineering firm. We are far behind you in exploring sustainability. So we started with LEED protocols or BREEAM, and now we are starting to embed some knowledge about embodied carbon, for instance, in our project and so on. With reference to the process, from your experience, is more important to have a process, so starting evaluating things at the earlier design stages, comparing, or having some more accuracy of the data? Because you mentioned ICE database, which we know is not very updated. Is not so. But if we focus on that and not on the process, the risk is that looking at the very end of the process.
That's a good question. I think both of those approaches, where you do a high level calculation and where you do a detailed calculation, are equally important. They would not replace each other, but I think it's when you use which approach is important. At early stage, for instance, we say the intention is we want to use the right materials that reduce the embodied carbon of whatever you're going to build. At the later stage, you look at more detail, more granular, so you could optimize it. That's when you reduce the targets furthermore. It's fine tuning your design. But in the key decisions, you should always be looking at the biggest benchmarking. You should know by using X material, I will be able to reduce my roughly the embodied carbon of the building, and then later on use the detail to fine tune. So I would say use both, but in a timeline as a combined process. Yeah.
Okay. Any question? I think so. So thank you so much, Owen Sam Brown, Shika. Very interesting your presentation. Thank you for all for coming here, of course. And so see you next time. Thank you.